Europa has an ocean larger than all of Earth's oceans combined. It has never seen sunlight. It has been there for 4 billion years. And in 2024, James Webb found something moving from that ocean toward the surface that no model predicted. Beneath Europa's frozen crust lies a sea so immense it defies ordinary scale. The ice above is thick, at least 15 kilometers and possibly twice that in places. Yet the water below stretches far deeper. Imagine a single sheet of ice taller than Mount Everest, blanketing an ocean that plunges down 100 kilometers, uninterrupted by land, darkness pressing in from every side. The numbers alone are staggering. Earth's oceans, all combined, fill about 1.4 billion cubic kilometers. Europa's hidden ocean holds at least twice that, over 2.5 billion cubic kilometers by the most recent estimates. That means more liquid water in one moon, orbiting Jupiter, than on our entire planet. Picture draining all the seas, lakes, and rivers from Earth and pouring them into Europa. The moon would still have water to spare. Its ocean wraps the whole globe, a saltwater shell nearly 10% of the moon's total radius, pressing against a rocky mantle below. The pressure at the base would dwarf anything found in Earth's deepest trenches. There are no continents, no islands, only a world-spanning abyss sealed beneath ice. The sheer volume raises questions that numbers alone can't answer. How does so much water remain liquid, locked away from sunlight for 4 billion years? What forces keep this vast alien ocean from freezing solid in the cold of deep space? The answers begin with energy, an invisible engine hidden from view that stirs the darkness below. Jupiter's gravity does not simply hold Europa in orbit. It kneads the moon's entire body with relentless force. As Europa traces its slightly oval path around Jupiter, the giant planet's pull stretches and relaxes the ice and rock, flexing the moon every 3.5 days. This tidal flexing is not gentle. It bends the crust by as much as 100 meters, generating heat deep within the ice and the rocky mantle below. The effect is like squeezing a stress ball. Friction inside Europa's layers converts orbital energy into warmth, enough to keep the ocean from freezing solid despite the sun's distant chill. Measurements show that Europa's surface radiates about 1 to 2 watts of heat per square meter, comparable to the energy released at Earth's mid-ocean ridges, but spread across an entire world. Models of Europa's orbit and internal structure suggest this heating has persisted for nearly 4 billion years. The Moon's resonance with Io, another of Jupiter's satellites, continually pumps energy into Europa's orbit, preventing it from settling into a circular path and shutting off the tidal furnace. This steady, invisible engine has profound consequences. Without it, Europa's ocean would have frozen solid eons ago, entombed beneath ice thicker than any glacier on Earth. Instead, the water remains liquid, cycling heat and, perhaps, chemicals between the seafloor and the crust above. The sheer longevity of this process raises a question that echoes through every layer of Europa's interior. What kind of chemistry, sustained for so long in the dark, might be unfolding beneath the ice? Tara Regio stands out like a scar on Europa's otherwise smooth white face, a region of fractured, chaotic ice that seems to have been churned up from below. Here, the James Webb Space Telescope has delivered its most surprising result: a sharply concentrated band of carbon dioxide, mapped at a wavelength of 4.27 microns, with a signal-to-noise ratio near 17. The carbon dioxide is not smeared evenly across the surface, nor does it match the patterns left by external impacts or Jupiter's radiation. Instead, it pools in the youngest, most disrupted blocks of Tara Regio, precisely where the ice shows signs of recent upheaval. Dr. Laura Miller, one of the principal investigators, describes it as a fingerprint, evidence that carbon-rich material has traveled upward from Europa's hidden ocean and frozen in place. The measured column density reaches nearly 3 times the maximum that could be produced by surface chemistry alone. No known process at the surface, not even the relentless bombardment of charged particles from Jupiter, can account for the strength and sharp boundaries of this carbon dioxide signature. The numbers point to a source beneath the ice, pushing material up through fractures and chaos terrain. For the first time, the data reveal a direct chemical bridge between Europa's ocean and its surface, a sign that the world below is not sealed off, but in active exchange with the world above. Hydrogen peroxide glistens faintly in the fractured ice of Tara Regio, its spectral signature peaking at 3.5 microns, a clear signal in the James Webb data, rising well above the noise. The detection holds a signal-to-noise ratio close to 12, high enough to rule out chance. This is not a random patch. The peroxide clusters alongside the same chaos blocks where carbon dioxide pools, suggesting a shared history. Peroxide on Europa is not just a byproduct of radiation. It is an oxidant capable of fueling chemical reactions if it finds its way into the ocean below. The presence of hydrogen peroxide, mapped precisely where the ice has been most recently overturned, hints at a cycle, surface chemistry feeding into the depths. Salt hydrates add another layer to the story. At 4.55 microns, a faint but unmistakable absorption betrays the presence of magnesium sulfate and other briny minerals, their spectral fingerprints matching laboratory standards. These salts are not evenly spread. They concentrate in the same disrupted terrains, reinforcing the idea that brine from the ocean is reaching the surface, freezing in place, and leaving behind a chemical record. Independent lines of evidence, peroxide, salts, and carbon dioxide, all converge in Tara Regio, painting a picture of active exchange between Europa's ocean and its frozen shell. Dr. Miller describes it as a chemical conversation, carried out in ice and light, waiting for a closer look. Ultraviolet glimmers above Europa, first hinted at something stirring beneath its frozen shell. In December 2012, Hubble's spectrograph caught a sudden surge of hydrogen, Lyman alpha, and oxygen emissions over Europa's trailing hemisphere, signals that sunlight and Jupiter's own glow could not explain. The data suggested a plume of water vapor rising up to 200 kilometers, with a density of roughly 1.5 times 10 to the 7th molecules per square centimeter. But the plume was fleeting, appearing only as Europa crossed Jupiter's bright edge. 4 years later, Hubble tuned its gaze for brief outbursts and caught another spike, a haze of ice grains reaching 250 kilometers, drifting eastward in a diffuse cloud. Yet the evidence remained ambiguous. Some scientists pointed to Jupiter's auroras as a possible source, while others saw patterns matching sporadic venting. Reanalyses trimmed the numbers, but could not erase the anomaly. Hubble's ultraviolet measurements pressed against the limits of certainty, leaving Europa's ghost plumes unresolved. The mystery now fuels Europa Clipper's mission to sample a plume directly and finally test the truth. Europa Clipper will sweep lower over Europa's surface than any spacecraft before it, tracing arcs just 25 kilometers above the fractured ice. Each of its 49 close flybys is a calculated brush with danger and discovery, engineered to pass through regions where plumes or surface venting are most likely. The spacecraft's suite of instruments is built for precision. Mass specs can detect organic molecules in concentrations as low as 10 parts per trillion, while SUDAR is tuned to analyze single grains of ice and salt ejected from the Moon. During a plume encounter, Clipper will sample vapor and dust in real time, capturing a direct taste of Europa's ocean without ever landing or drilling. The detection thresholds are set so low that even a faint, fleeting plume, one carrying a few thousand molecules per cubic centimeter, could yield a full chemical fingerprint. For the first time, scientists will have the chance to match surface chemistry with subsurface material, closing the loop between remote sensing and physical evidence. Life on Earth depends on sunlight, but Europa rewrites the rules. Here, in a world locked beneath ice, energy comes from within. Tidal forces need the moon, driving heat and chemistry in total darkness. If the ocean below the ice is truly active, cycling carbon, mixing oxidants and salts, and sustaining chemical gradients, then the basic requirements for life may be met in a place where the sun is just a distant point. Astrobiology rests on three conditions: liquid water, a source of energy, and access to the right chemistry. Europa now appears to have all three, but in a form that does not rely on a star. This possibility stretches the definition of a habitable zone far beyond the narrow band around the sun. In this new view, any ocean world with internal heat, a moon orbiting a giant planet, or an exoplanet far from its star, could offer a cradle for life. The search for biology is no longer confined to planets like Earth. It now reaches into the deep, dark oceans of countless worlds, waiting for a sign. Right now, Europa's ocean is not a distant idea. It is a chemically active world, stirring beneath ice. Each new signal deepens the possibility that conditions for life exist far from Earth. The search isn't science fiction anymore. It's happening, and the answers may be closer than we imagined.